A block is released from rest at the top of a fixed, frictionless ramp with horizontal length L and an inclination theta. For a fixed value of L, which value of theta minimizes the time needed for the block to reach the bottom of the ramp? So let's start by drawing a diagram of this process here. So here we're going to have the incline, and it's not very good, but here's how it would probably look like. The inclination is theta, and the horizontal length is L. So we know the horizontal length, but we don't know the total length. So let's call this total length L. Actually, I'm going to move it over here. Let's call this total length L, and I'm going to use sort of lowercase l instead. So the total length is going to be equal to the horizontal length divided by the cosine of the angle theta. And this is because the cosine is equal to the horizontal length over the total length. So we can just rearrange those terms to get this equation here. And also, we're going to need to figure out the acceleration of the block. So let's say that this point is the dot here. We're going to do something like a free body diagram, except this time we're only going to label the gravitational acceleration. The diagram will just simply help us decompose the gravitational acceleration into its component parts. So let's go ahead and do that. We can decompose it. This is the angle theta. So the gravitational acceleration down in the direction parallel to the ramp is going to be given by g times the sine of the angle theta. And this acceleration perpendicular to the surface is going to be given by g times the cosine of theta. Okay, so that is our acceleration. And now we need to relate these to the time. And we can do that with one of the kinematic equations. So if you remember, the displacement is equal to the initial velocity times the time plus 1/2 times the acceleration times the time squared. Okay, so time squared. And we can use this equation here. We know that the displacement is simply from the top to the bottom of the ramp. So it's going to be the total length of the ramp, which we can write as the horizontal length over the cosine of theta. Let me write this over here. The horizontal length over the cosine of theta. That's what we determined over here. And the block starts from rest, so it's released from rest, so this term, we can neglect this term. And we only have 1/2 times the acceleration, which we just found over here to be g sine theta, the gravitational acceleration, times the sine of the angle theta, times t squared. So we can rearrange this to solve for t. So t squared, let's start with t squared, is going to be equal to 2l over g times sine theta cosine theta. But I want to simplify this a bit. So let's try multiplying both the top and the bottom of this part by 2. Let's multiply both of these by 2. So if we simplify this, now we get that 4 times the horizontal length over 2. Actually, I'm going to write the 2 after this. Times g times 2 sine theta cosine theta. And that's equal to t squared. And let's take a look at this here. Now, if you remember, the sine of 2 theta is equal to 2 sine theta cosine theta. So that's the double angle identity for sine. And so we can use this to simplify this to 4 times the horizontal length over g times the sine of 2 theta. And remember that this is before we, this is for t squared. So to find t, we just take the square root of this. So the square root of that is going to be equal to 2 times the square root of L over G sine 2 theta. Okay, so I'm going to erase all of this to make a little more room for writing here. So let's get rid of all of this. So the time is given by 2 times the square root of the horizontal length over g sine 2 theta. Theta is the inclination angle. And again, the problem is asking for the value of theta that minimizes the time. So if we look at this here, we need to find a way to maximize the denominator. So we need to make this big. So if we make this denominator big, then we will minimize the time that it will take. So in order to make this denominator as big as possible, the sine of 2 theta must be at its largest value. So sine of 2 theta must equal 1. The maximum value of the sine function is 1. So we need it to be the maximum value to obtain the minimum time for the block needed to reach the bottom. So now we just need to simply solve that equation. So the angle theta is going to be the inverse sine of 1 over 2. So this is simply going to be 90 over 2. So the theta, the angle theta to minimize the time needed for the block to reach the bottom of the ramp is going to be equal to 45 degrees.